So in this lecture, we're going to walk through using a sampling distribution to answer a question. The question is posed right there. Pause the screen for a second if you want to read through it, so I don't have to. So hit pause now, read the question, and then we'll go through it. All right, so hopefully you've read through the thing, and we've got we want to find out, we want to answer, is this proportion of BMI students unusually small? What we need to know to answer that question is, okay, what are we talking about in terms of what is the behavior, or how do samples of, in this case, samples of 200, because we know this is a sample of 200, behave when we're being pulled from a population that has a proportion of 22% for BMIs of 25 or more. Okay, so we've pulled a sample from that population, and we want to know, okay, well, how likely is it that we would have gotten a sample that has whatever the sample proportion that we find is, right? So let's go through this systematically, kind of a step-by-step process. I think that helps folks, right? So first thing we want to do is we want to check the assumptions and conditions. Don't do anything with the normal model until you can prove that you can be using it, until you can speak to it, right? And this is something that we need to be looking at with regard to the, especially if you're taking the test, you have to speak to these things. So we're going to jump right down to the conditions, however, because sometimes the conditions are a good indication that the assumptions have been met, right? So if we're looking at, our first one is randomization, right? Well, the randomization, we're told that the sample is randomly selected. So since it's randomly selected, it should be independent and representative of the population, right? We're going to go on their word that they did it right to collect a random sample from the population. So randomization condition is met. Second one, 10%. Right. 200 is more than likely less than 10% of the women at a large college, right? This isn't just for purely for context. That is your way to work around that 10% condition. Like, yeah, we probably is. We don't know it for certain. We don't have the total number of people at the school, or we certainly don't have the total number of women at the school either. But if it's a large college, there's probably more than 2,000 women at the college. And then the success failure, don't just check. This is another thing where we don't want to just check boxes here. Both of these show that 200 times 0.22 and 200 times 0.78 are both greater than 10, which they are. So we have met the randomization condition, which also kind of spoke to the independent condition. A 200 sample is clearly large enough to have enough results to make a good histogram with. 10% is less than 10%, and we've got enough success failure. With all the conditions met, we can use the normal model to describe the sampling distribution. All right, now we can proceed with the kind of the work, right? And we're going to look at calculate the parameters, and I probably should say the parameters and the sample statistics and sample stats. Right. And sample stats. Right. So as always is the case, mean behaves just like we think it's going to mean. We would expect that if the population that we're pulling from is 22%, right? If the population proportion is 22%, and this is why that randomization condition is so important, if we have got a good representative sample, it should also be 22% of the sample has a BMI of 25 or more. So the mean of our sampling distribution, the center of our sampling distribution, is going to be centered around 0.22. Nothing to do with that. They're just take what you give, take what they give you. Standard deviation, we build it from that, okay, is the square root 0.22 times 0.78 all divided by 200. P times Q divided by N. N is 0.029. Probably should be a squiggly, maybe that might be actually 0.29, 0.029, but. And then the only other thing we need, because we've got a mean, we've got a standard deviation, we need a sample statistic. This is what we expect. We expect 0.22. Did we get 0.22? Not at all, right? Not at all. We got 0.155. But when we're talking about sampling, there's going to be variation, right? There's going to be sampling variation from sample to sample. What we're trying to determine is the difference between 0.22 and 0.155 more than we're willing to accept, more than we're willing to live with. That's what we're doing here in inferential statistics, right? We know we expect it to be around here, but it's not always going to be that. That's so, and we found it's this. So now we've checked the conditions. We've got a mean, a standard deviation, and a value. That should be your Q. That's why we want to be, so we're going to be using the normal model with a 0.22, a mean of 0.22, and a standard deviation of 0.029. Right? Now we're gonna start running some calculations. Right? We're going to use the normal model to find the probability. If you've got a mean, a standard deviation, and a value, z-score should be first and foremost coming. What we should be thinking. Right? So we want to find a z-score, and it's just like we did before. Now, in our formula sheet, we have a general description for a z-score. Okay? A general description for a z-score, but it's going to change. It's going to get dressed up a little differently each time. So it's important that we recognize that what we're trying to do, we're taking our value, subtracting some known mean or some presumed mean in this case, and then dividing it by some variation of the standard deviation. Right? We might dress it up a little differently depending on what we're doing and depending on what we have, but it's always going to be falling back to that. So right now, we do that out and we get a z-score of negative 2.24. Shouldn't be a surprise that it's negative. Remember what we're trying to. This is kind of the z-score review here. According to our distribution, is 0.22 is the middle, and we're trying to find, okay, what's the likelihood that we get a sample of 200. These are all the behaviors of the 200, right? Of the samples of 200 pulled out of this population. What percentage of those are going to be 0.155 or less, right? So this is quote unquote the work. I mean, it's not a ton of work. The calculator's doing it all for you, but you got to show this. Maybe not this part. Maybe not this part, but definitely you want this in there. That needs to be included. And then we want to write two different probability statements. We want to find the probability that the sample proportion is less than 0.155. That's what the question is really asking us. So we've translated this context into a probability. But we don't use that. We use z-scores. So we want to make sure that that probability is going to equal the probability of z is less than negative 2.24. And then they don't care how we get this number. But it's normal CDF because it's a normal model. And since this z-score is negative 2.24, and then this z-score way down here, right, is negative 10, I'll put negative 10, negative 2.24. That's in our second vars, and we get this, very small probability that we'd get this. So our conclusion, remember, this doesn't tell anybody anything, right? Because nobody's going to understand that. If you say, is this proportion of high BMI students unusually small, and you say 0.0125, that's not going to mean anything to anybody unless they're looking at the same statistics you are. So make the conclusion. The sample proportion the sample proportion of high BMI students would only occur 1.25% of the time. So it is unusually small, right? If, and I'm saying this because it's kind of a sneak preview, if this actually is the percentage in the population, 0.22, we're going to see something as small as 0.155 only about 1.25% of the time. So something's up. Either our numbers are off or this actually is incorrect. One of these is wrong. Not wrong, but might be slightly different. Okay. But again, we use the sampling distribution to determine, okay, how can I get to the normal model? But once you do that, it's just a normal model problem, which is hopefully, it's pretty straightforward. All right. So we're going to get plenty of practice with doing these as well. So whatever we can get to in class to practice or for homework, take advantage of it. Let me know if you have any questions. I hope this helped.